The purpose of this exercise is to see what happens with an initial guess. We have here the graph of some function, and for each initial approximation, we're to determine graphically, it means we're going to draw on this, what happens if Newton's method is used for the function whose graph is shown. And for part A, we're looking at x1 is equal to 0. So suppose we make x1 equals 0 our initial guess. The idea is there's a tangent line to the curve at that point. That tangent line has an x-intercept. That x-intercept is associated with another point. That point has a tangent line. And as this process continues, we're not going to get anywhere near an x-intercept. So that's what happens when we pick x1 equals 0. I've got a clean copy of the picture here now, and suppose we start with x1 is equal to 1. We have a point on the curve, but the tangent line is horizontal. We're done. Starting again, suppose we start with x1 is equal to 3. Associated with that point on the curve is a tangent line. Let me fix this. That tangent line has an x-intercept that is either 1 or it's just to the left of 1. Let's suppose it's just to the left of 1. Then I'm going to end up pretty much like the first case, right? I'm going to end up over here and then a tangent line over there. It's a little off, but you get the idea. This is starting to get a little frustrating, isn't it? So let's look at x1 is equal to 4. One of these has to work, right? Well, it's not going to be 4. We can see that associated with x1 equals 4 is a horizontal tangent. If x1 equals 5 isn't a good guess, then we have to give up, right? So suppose we start with x1 equals 5. There's a tangent line that has an x-intercept that gives me a point on the curve, associated with which is another tangent line. I think that's about there. And then we're starting to get to this x-intercept there. So the point here really is if you're doing Newton's method and you start getting numbers that are farther and farther from where you expect an x-intercept to be, or you happen to pick a place where the tangent line has a horizontal slope, the derivative is 0, then you're not going to get anywhere. And when you're picking an initial point here, sometimes it is useful to look at the graph of the function. It's kind of what they do in the real world, and then go from there. Now we're going to do an exercise here. We're going to use Newton's method to approximate the square root of 2 accurate to 6 decimal places. Well, I know that the square root of 2 is a 0 for f of x is equal to x squared minus 2. We know that because we can set x squared minus 2 equal to 0, and then I'll get that x squared is equal to 2, and so that x is equal to plus or minus the square root of 2. As I was just saying, it would be useful to start with a graph. And I don't need the graph to be perfect, but I do need it to be reasonably accurate. You can see from the previous example why. So this is not by any means a perfect parabola, but it seems like x1 equals 1 would be a good start. Newton's method requires us to find f prime. So f prime of x here is equal to 2x. And then it's kind of usually, like I see it often as like a table. So x sub n, and let's just remind ourselves of what x sub n is using the recursive formula. It is x sub n minus 1 minus f of x sub n minus 1 divided by f prime of x sub n minus 1. So the pieces that I need are the function value and the derivative, and then this arithmetic, right? So maybe it would make more sense to say f of x, or x sub n minus 1 here, and then f of x sub n minus 1, and then f prime of x sub n minus 1, and then those together can give me like x sub n, which is what we already said. Now I said we'd start with an initial guess of x1 is equal to 1, And now I'm going to look at f. F of 1 is negative 1. F prime of 1 is equal to 2. And x sub n minus 1. So we have 1 minus a negative 1 over 2, which is going to give me 3 halves. That now becomes my new input. Now for x equals 3 halves, f of x is going to be 1/4, f prime of x is going to be 3, and then x sub n is going to be 3 halves minus 1/4 over 3. This is equal to 17/12 or 1.416 with the 6 repeating. Using now 17/12, I'm going for the exact value for the input when I can. Using 17/12 as my next input, I end up with 1.414216. I'm getting the decimals because we're supposed to approximate this accurate to 6 decimal places, and just the fractions aren't telling me how close I am. Well, we're almost there. I happen to know that square root of 2 is 1.414213. But how would you know it's time to stop if you don't happen to know that? Well, I wrote down a couple more rows of this process. And if we're looking for accurate to 6 decimal places, what I'm looking for is everything up to that 6 decimal place matching up. Once that happens, then I have my answer. Now, this is incredibly tedious, and you can see that I switched from fractions to decimals at some point because the fractions got really out of hand. The decimals weren't really fun either. Next, we're going to see how to use Excel to do this in a much more efficient manner.